Welcome to solverfy.
Okay, in this problem, we are asked for a number of things. We're given a wave function, which is a function of x and t, which is some mixture of complex exponentials, so we have some oscillating behavior occurring. We're first asked to find the probability density, which is the square of the wave function. We're then asked to find the first two x values, which give maximum probability density for both time equals 0 and time equal to 2 pi over omega, the angular frequency. Once we've done that, we are asked to compute this average velocity, which is computed by the change in a particular x from t equals 0 to t equals 2 pi over omega over the delta t. And we're asked to compare this to the VAV from the first example in the chapter. So the only real equation we need to know is that the probability density is defined as the square of the wave function. And in particular, it's not simply a square, it's the original wave function multiplied by its complex conjugate. And in this problem, we actually have some complex values, so we actually need to be careful about using that complex conjugate correctly. So let's start this up. It's going to be a fairly long problem, many parts. So because we're dealing with complex exponentials, it's going to actually be more useful to keep them in that form and maybe perhaps at the end convert them to sines and cosines using Euler's identity. But let's just start by setting this up. So this square, as we mentioned, is the wave function multiplied by its complex conjugate. So let's write this all out. The original is simply e to the I kx minus vt. This is a mixture of two different oscillating functions, which are moving in space and time. That's what makes this kind of difficult. So recall, to do a complex conjugate, well, let's add one more parenthesis. To do a complex conjugate, all you do is add negative, change the sign of everywhere you see a complex number. So we have i's here and here. So we're going to put negative signs on them, and that's essentially how we do a complex conjugate for a function. So we see that we're going to have to be multiplying two-term quantities. So we're going to end up with a lot of terms, unfortunately. But it will simplify down nicely. We have to be super careful about how we do this exponential math. So remember, multiplying exponentials, we have to add in the exponent, and we need to be really careful about how we deal with I. So I'm not going to show everything because this would be too many steps, but we end up with a squared, of course, because the a's multiply. And we end up with let's see how many steps to show. After a couple of steps, so I'll leave that to some exercise of the reader. But I think it'll be pretty straightforward how this happens, just doing some exponential math. We end up with a 1, which appears twice, and they add together to a 2. We have this second term and this third term. Okay. And that's it. At this point, I think it's useful to use Euler's identity. Recall e to the ix equals, we can express as a cosine x plus I sine x. That's just a Euler's identity, Euler's formula. So we can actually convert this into some sines and cosines, make it a little bit easier on ourselves, do a little bit of simplification to actually get a better feel for what this function looks like in x and t. We end up with something much more straightforward, which we can actually deal with. This is it. This is our probability density. It's a cosine, which is evolving in t and x. And that's it. So first things first, we can locate some local maxima for t equal to 0. So when t is equal to 0, this probability density collapses down a little bit to cosine of negative kx. And because cosine's an even function, we can just say kx. It doesn't change the sign or anything. So by the nature of the cosine function, we know this is maximum when the argument of cosine is pi, or it would make the cosine the most negative, make it equal to -1, which, subtracting a negative from a negative, that'll give us a maximum result. So essentially we want kx, this argument of the cosine function, to be pi. Thus, one place where we have a maximum would be pi over k. And the next place where this cosine's at a minimum, and thus the whole thing's at a maximum, is when kx is 3 pi. Okay. When that would give us a 3 pi over k. So those are our two x values that would give us maximum probability density for time equal to 0. Now let's do it for time equal to 2 pi over omega. Yep, 2 pi over omega. Plug it in. Our probability density function, call it p of x, is going to be equal to, in this case, a squared 2 minus 2 cosine of 6 pi v over omega minus kx. So same thing, we want to minimize, we want cosine to be the most negative so that when it multiplies by -2, it makes this the most positive. So we want the argument 2 pi v over omega minus kx to be pi for the very first one. Solving for x, we get pi over k multiplied by 1 minus 6v over omega. And doing the same thing for 3 pi to give us a second x value, something very similar. Pi over k, 3 minus 6v over omega. Those are our two values for the next time step. So now let's get this v average, which is simply the change. We can take one of our x values for the time equals 0 case, and then for the time equals 2 pi over omega case, take the difference over the time difference. That should give us some average velocity. So let's do the first one for both cases. So we would have pi over k, 1 minus 6v over omega. That's for case 2, when time's increased. Now for time equals 0, we're subtracting by pi over k. So this is describing the movement of a maximum probability point in time. And the time difference is obviously 2 pi over omega. So we collapse this fraction down a bit, and we end up with 3v over k. All right. So we were asked to compare this to this result from an example. In which VAV was 4 omega 1 minus omega 1 over 2k1 minus k1. So in that example, we have to be really careful. We have a wave function that looks basically the same, except we look at the argument inside the complex exponentials. We found, you will see that if we keep things as close as possible in our example, the k2 would end up being 2 times the k1, and the omega 2 would be 4 times the omega 1. So as long as we keep that all the same, we plug these in for k. Ooh, missing. There's one thing we're missing. Nope, that's it. Yeah, keep all those things the same. We plug them in. We will end up with this 3v over k as before, or same kind of thing, except the omega is now v. That's we're trying to keep this as analogous as possible. But you'll see that these actually are comparable to each other. Ends up being the same kind of result. We had to just go through a lot of math to get there. So that's it.